mixture of experts model has shown to work better than big dense models a lot of time. So what if you have a big dense model and instead of training a mixture from experts from scratch, you want to just convert it into a mixture of experts? This is what this research paper explains. And then you can continue training it as mixture of experts. So we have all of the data here, all of the information is gonna be very interesting and fun. Very little mathematics, it's easy to understand. Dense layer is a big normal, the usual neural network. And mixture of experts is when you have a bunch of small neural networks, each is expert at some knowledge, and then you have one network that's choosing which neural network to use based on like the question. So if you want to convert big pre-trained neural networks into a mixture of experts neural networks, there is not a lot of research, but this paper is the research that you need and they will show you how to do it. That's what they say in this intro, and they call this conversion upcycling. So upcycling from a dense layer to mixture of experts. They will show you how to do it, and they will show you a study on best hyperparameters, so learning rate, batch size, and load balancing loss. We demonstrate that our upcycling approach produces a better model than continued dense model training. So if you just stop training the dense model and then continue with their method, it's gonna be better than if you continue training. And they experiment on the same token, same model size. One, they just train the dense model all the way, and the other, they train dense model a little bit, and then they switch to their method. And their method shows better result than the one where they just trained dense model all the way. The purpose of that is to show that you can take already existing big dense models and just continue with their method. They also tested this softmax-then-topK rounding, and it improves over topK then softmax approach. And higher granularity MOEs can help boost model accuracy in certain training scenarios. And then for experimentation, they take this model, Nemotron 415B, and then they train it on 1 trillion additional tokens in 2 experiments. In the first experiment, they just continue training the dense layer. And then in the second experiment, they use their method on converting it into mixture of experts. And same model, same number of tokens, and the improvement is about 2% on MMLU. You see here 65.3 and 67.6% for the mixture of experts model. This shows that improvement does not just come from more tokens, like training it for more, because they train it for more in both ways, but the MOE architecture wins. Upcycling is the approach of converting a trained dense model into a mixture of experts. So let's say we want to convert a dense model into 10 experts, for example. Well, not to lose any accuracy, we're just going to copy that exact same model into like 10 times. Here we see expert 1, expert 2, expert n. Each one is same as the feed-forward network, our dense model. Now, let's say we want to, for each token, we want to choose 3 most likely experts who are best for this particular token, for the next token. We have a router that's going to choose out of those 10, 3 most likely. So the router is going to give us probabilities. And here, from I1 to T, and our T is 3, because we are choosing 3 experts. We are going to calculate the output of that expert, the probability token distribution that expert gives, and then multiply that with the probability for that expert being chosen. And then sum up all of those probabilities, and that's how we get our MOE activation. It's also well explained here, so you can pause and read if you didn't understand. They also find out that it's better to reduce the dimensionality of these MLP layers of these experts from the initial big dense layer, and then route tokens to multiple experts, than to route tokens to just one expert while keeping the dimensionality. And the reason they are reducing the dimensionality and then routing to multiple is not to increase the computation, or to increase the computation only a bit. Because if they started to route to multiple MLP layers without decreasing the dimensionality, then that would just double, triple computation required in comparison to the original dense model, because it was just duplicated multiple times. So this is called granular MOE. Then they also have this issue of softmax-then-topK ordering. So classically, how this works is we have some input token, we have this router matrix, and we multiply it, and then we apply softmax. So this will convert this result of this multiplication into probability distribution. And then we just select, for in our case, like 3 most probable experts for this input. So top K is going to be 3 in our case. So this is the traditional way. The problem they experience with this traditional method is that as soon as they convert dense model to mixture of experts, the outputs change. They are not even very similar to the outputs when when it was just a dense model. So that's a problem, and it should remain relatively the same, or almost the same, or same. And they say one potential way to fix this is to continue training this mixture of experts model just a little bit, and it should return to the outputs that are same or very similar to the dense model. Another way to fix it is to swap, to first calculate, like take top K of the pure logits and then calculate softmax. So with this method, the outputs are very similar, almost or same as when it was dense model. But the problem here, information contained in the absolute magnitude of the router output is lost. And top K must be more than 1, because otherwise you cannot, because softmax of a single element is a constant 1, which has no gradient with respect to the input, so you can't backpropagate it. This technique is used in Mixtral. They're gonna try training with both techniques and see which one works better. And then, again, as I said earlier, it has recently been suggested that increasing the number of experts to which a token is routed to, while shrinking the dimension of each expert, might be a superior approach to keep the computation same. This is called granular mixture of experts. Here's what you can do. You can take this big dense layer, just divide it into shards. So as I understand, sharding just means slicing it like pizza, basically. So you want to slice it into 8 different shards. You just slice it into 8 different shards, different parts. And then what so for example, what you could do is multiply each of those 8 pieces 8 times, and now you got 64 experts. So each of 8 of them is the same. So the problem with this is if you want to route, like if you want this to have same behavior as the big dense layer, then the router needs to select like these exact 8 different ones, and then to combine them together to have the same behavior as the big dense network. There is also this other issue that I didn't quite understand, but they explain how it, like the idea, but the conclusion is this implies that the expert outputs are scaled down by a factor of 64. It's important to also mention that as soon as they convert this to mixture of experts, they wanted to keep the same like kind of outputs, same behavior as the big layer. The way they solve this problem is using what they call virtual group initialization. So they just make sure that in the beginning, as soon as they convert it to mixture of experts, the router can only choose between groups that contain one of each of the different like parts of the dense model. So whatever group they choose, each group is going to contain all 8 different parts, so it contains the whole model, so it behaves exactly the same as the dense model. Now during the training, all of this can change, but it's just important that in the beginning it keeps the same behavior. Then they talk about scaling the weights. Now I must admit this is like too complex, too dense for me, so I could not understand any of this. All I could understand is it's better to scale both sets of weights, W1 and W2, than just the second set, but I don't understand why, and I don't understand like this how, so maybe you can take a look at yourself, or maybe somebody can explain in comments. In the results, they first explain how the model is built. They use a rope, they use a swish activation function and gated linear unit. and then they explain about data. Upcycling can be performed on either pre-training data that the pre-trained dense model has already seen, new unseen data, or a combination of both. In this graph to the left, we can see two models. One is just they continue training the big dense model, and the other example is when they upcycled, created a mixture of experts. And you can see that the blue line actually starts to plateau, while the green line loss reduces. So this is loss, I forgot to say. So it looks like mixture of experts works better if you convert it to mixture of experts. Also, if you have a fixed compute budget, smaller compute budget than the training of the dense model, then they show here that it's better to just upcycle the trained dense model and continue convert it to the mixture of experts than to try to train mixture of experts from scratch. Now it does kind of make sense because then the first one got a lot more training actually because it's just a continuation of the dense model. What they didn't answer in this research paper is what if you have a large compute budget? Is it better to train mixture of experts from scratch or to continue on top of the pre-trained dense model? And then you spend the same budget for continuation and from training from scratch. So here you can see that if you're training MOE from scratch, the loss starts very high and then it reduces. And then for the same compute budget, you just continue from this loss from the dense model and then it goes a lot lower. And if we take a look at this, so I believe this is where we should measure, at this point. And then this loss here is a lot lower than this loss. Now, I'm not sure why this line goes all the way here. Maybe this is what we should measure, this point against this point. So I'm not sure which points, but anyways, both of the points of the loss are lower. And for future research, they leave the following question. If you have a dense model and then you have a large compute budget in comparison to the pre-training of that dense model, should you continue to just convert it to MOE or should you train MOE from scratch? So which one is better? Now let's talk about learning rate. As the dense model is trained, it starts with a big learning rate and then it reduces the learning rate during the training, so it converges to a local minimum. Now they are not sure, or they are trying to see three following examples. They use the constant learning rate, so wherever the dense model has finished with which learning rate, they just use that as a constant and continue with the MOE training, and that's how typical fine-tuning is done. Another option is to set the learning rate same as the beginning of the pre-training of the dense model, and then the learning rate at the end of the pre-training dense model will be at the end of training a mixture of experts. So for example, if the training of mixture of experts is 10 times smaller than the dense model, then the learning rate will converge 10 times faster to this smaller value. So the learning rate starts the same in dense and mixture of experts and ends the same in dense and mixture of experts. And the third thing they try is using learning rate in the beginning of mixture of experts training that's smaller than learning rate in the beginning of the dense model, because if you use as big of a learning rate, it can lead to catastrophic forgetting. So where everything in the model gets mixed up and destroyed. And then the ending rate of MOE is same as ending rate of dense model. The first option is low constant learning rate, where you just continue the learning rate from when the dense model finished. And you see the loss actually is a lot smaller in the beginning, but then it plateaus and it doesn't keep learning more. So this is not good, it seems, and it seems like it doesn't learn anything much at any point here. The green is the second option, where you have the same loss in the MOE as in the dense, in the beginning and in the end. And the blue is the third option, where you have in the beginning of MOE half of the loss as in the beginning of the dense, and then the ending is same loss. And we can see that the second option starts with a very high loss, but then it converges. And the third option starts with lower loss, but then it converges to the same thing. So from this graph, my understanding is that this blue, the third option, is the best one. Now, I'm not sure what would happen if they continue training. Would like one of these losses like converge even more? But since their learning rate is same here, I would suppose that it would just like remain the same because the learning rate is same here. Here we can see how the learning rate decays. So this is the second option, the third option, and this is the constant one. Interestingly, using a peak learning rate as high as pre-training, so this is the second option, does not lead to catastrophic forgetting. Let's talk about weight similarity. So typically when you fine-tune a model, the weight similarity between the cosine similarity between weights of the fine-tuned model and the pre-trained model are usually close to 1. So it means the weights are very similar. And what they do here, well, there is not just one dense model, there is a bunch of experts. So the way they measure cosine similarity here is that they measure cosine similarity with each expert against the dense model, pre-trained dense model, and then they average out the results to find average cosine similarity. But cosine similarity means that weights are very similar, and that may not be a good thing because here we are trying to train the model further. So here we can see that in the first option, with constant learning rate, cosine similarity is close to 1. So it seems like the model of the mixture of experts model is very similar, if maybe even almost the same as the dense model, which was not our goal. Our goal was to train the model to be better, to be different. And with the second and third option, where learning rate is varying, we see that cosine similarity is between maybe 0.6 to 0.775. Which the authors believe that this implies that bigger, like varying learning rate, help the model escape the local minimum of the dense model and find superior, better local minimum, and then converge there. And now weights are different from the weights of the dense model. So since weights are a bit different, but the loss improves, that means like model learned new things. Now batch size also has a large impact on this method for two reasons. Since each expert receives only a portion of tokens, gradients are noisier than the dense model. The load balancing loss is noisier if there are fewer tokens to balance. So here we can see the batch sizes, 8,000, 500, and 1,000. And they found that loss is improving same as 512 and 1,024. So 8,000 it's not improving as well. And the conclusion is that increasing batch size to 1,024 or 4 million tokens, and for each of these batch sizes they have different number of tokens as well. So let me show you, these are batch sizes and these are the corresponding tokens. But basically if you double to 1,024 batch size, it does not degrade accuracy while improving model flop utilization. Then load balancing and regularization loss. We found that while not using auxiliary loss at all leads to dead experts and causes the training loss to plateau early. Auxiliary loss coefficients set too high leads to auxiliary loss overwhelming the language modeling loss. We found that auxiliary loss coefficients between 10 to minus 2 and 10 to minus 3 to give the best language model loss. They also found that z-loss does not influence these experiments, so they are not using z-loss and they are using auxiliary loss coefficient of e or of 10 to minus 2. And this is the graph that shows z-loss, so without z-loss blue, with z-loss green, and it's the same, and so they're not using it. Softmax-then-topK order, we consistently found that using softmax-then-topK works better than topK than softmax. For upcycling. We hypothesize that this is because the softmax-then-topK approach preserves the information contained in the absolute value of the router output. However, keeping the output of the original upcycled model similar to the output of the dense model is more difficult with this approach because the outputs no longer sum to 1. We overcome this issue with our weight scaling method. Then there is a graph for weight scaling, which I did not understand how it works, but basically using weight scaling helps achieve better loss when upcycling Nemotron 415B into 8 experts top 1 MOE. Then let's take a look at the granularity. So here we have 64 experts this has 8 experts, then this one has 128 and 256. And when you go from 8 experts to 64, there is a significant improvement in loss. But then there are diminishing returns, because when you scale further from 8 to further, the returns are actually almost, the loss is almost the same. Now let's take a look at the granularity. So here the gray one is 8 experts top 1. And then the green one is 64 experts top K. So there is 64 experts, and then each of the experts is smaller. So they take roughly the same compute. So you take 8 experts from 64, it should be the same compute as 1 expert from 8 experts. So this is just divided into 64. And they found that actually it's better to have the green one, there's a lot of experts, more granular, 64 experts. But then as you keep scaling the experts, 228, 256, there are diminishing returns. So there is no need to scale further because the loss is almost the same. Then let's see what happens if we compare 8 experts top 1 and 8 experts top 2. So each token is routed to 1 expert, and then here each token is routed to 2 experts. Now this requires more computation because you have 2 experts. And then loss here decreases when you have 2, so it's smarter if you have 2 experts. And then this is the same graph but for different models, so this model and this model. So 2 experts is better but more compute. Same here, 64 experts top 8, 64 experts top 16. Top 16 is better. And 64 experts, same thing but for different model. Top 16 is better but more compute. And it's not exactly 2 times more compute because this is just doubling the experts, but there are other things that require compute that are not doubled. Now they experiment with shared experts. So the idea of shared experts is a few experts in the MOE are always activated, and they learn common knowledge that usually would be learned by all of the experts, because there is some knowledge that needs to be learned by this common knowledge. So they just use these experts, they are always activated, so the other experts do not need to learn all of this common knowledge. And then they experiment here, 8 shared experts and 64 top 8 versus 64 top 16. Now the amount of experts is always the same, because here 8 are always activated and then 8 get chosen, and then here 16 get chosen. And they found that there is no improvement. So that's why they did not use this shared expert methodology. So now let's see large-scale upcycling. Let's just look at the table. We have this model. This is just a dense model before any continuation. It has this validation loss and this MMLU score. So if we just continue training this dense model without converting it, upcycling it, then the validation loss improves, MMLU improves as well. And then we have 2 different MOE architectures. We have 8 experts, 8 groups, which is 64 experts, top 8. And we have 8 experts, top 2. So these are also supposed to be smaller experts. So the compute on this and this is the same. This just has increased granularity. And validation loss is smaller here. So top 8 experts, top 2. And the MMLU score is higher here on this particular method. But as I remember, sometimes 64 experts top 8 works better than this one. So maybe just in this case it worked better. Okay, I found the difference. So we see here 64 experts top 8 works better than 8 experts top 1. But down below in the table we have 8 experts top 2. So I think we are using more compute. That's why it works better. So we have 8 experts top 2. Then in the related work section below, they just talk generally about mixture of experts research. If you are interested in more research paper videos, I'm gonna make videos on a bunch of these new research papers that are very interesting, and you can check my channel here. I'm gonna be making a bunch of these videos. Thank you for watching and see you in the next one.